Okay, so when last we met, we had been talking a little bit about Schrodinger's equation and about tunneling and all of this kind of stuff. So sort of the last piece of this puzzle is Heisenberg's uncertainty principle. And this is where we really get into the idea of you can't know the position of a quantum system precisely. Because now we know that light and matter interact. So energy and matter interact with each other. And what that means is if you try to take a measurement of these very small systems, you're going to change them. So Heisenberg said the more precisely you try to measure something, the more you're going to affect the system. So if you try to use light to very precisely measure the position of an electron, you're going to move it and you're going to change its momentum. Or if you're trying to measure its momentum, you're going to change its position. So there is a trade-off between how well you know one or the other. You can't know either one of them precisely. You can only know them within a certain range of value. So that's why we get into this concept of, well, it's probably, or the probability that it's in this location is this much, but we can't know exactly where it is. So that's why I say when I talk about the electron cloud model, that the electron cloud model is a cloud of probable locations rather than the specific location like the Bohr orbits were. Excuse me. So this really only impacts very small scale systems where you can affect this change by doing the measurement. And so the two values that are in competition here are the position of the particle and then its momentum, which is its mass times its velocity. So you can't know exact values for these things. You can only know them within a certain minimum range. Okay, and basically they're order of magnitude values. Okay, and so it's related to Planck's constant and how the product of those two values has to be larger than a factor that contains Planck's constant, so 10 to the minus 34. And so you can know them pretty well, but when we're talking about the product of these two things, that kind of narrows down exactly how well we can know each one of these values. So that's, you know, that's kind of the final piece of the electron, the idea of the orbits, the electron cloud models. So in chemistry, when you had chemistry, you probably learned about the different quantum numbers and how, you know, these quantum numbers are what determine the shells and the orbits and how things fill up and all of that stuff. Well, the physical basis behind those is based on the concept of orbital motion and angular momentum. And so what it does is it describes the uniqueness of these energy levels based on how many protons are in the nucleus, what the interaction is and the spacing, but also how you can fill up these available orbits with electrons, because it turns out that there's rules about how close two electrons can be in the same energy within an atom, and that's what Pauli's exclusion principle defines. So two electrons cannot share the same energy in the same atom. So the quantum numbers are basically a description or an address of the energy value of that particular electron, and they have to be unique. So it's just like parking lot spaces, you know, one car per one parking lot space, and two cars can't share the same parking space in the same parking lot. Okay, so the quantum numbers, you already probably know what they are. You've got N, the principal quantum number, L, the orbital quantum number, M sub L, which is the magnetic quantum number, and then M sub S, which is the spin quantum number. Now, N, L, and M sub L are all interrelated. And then M sub S is kind of its own little entity, but it only has two possible values. Okay, so N, L, and M sub L all have to do with the angular momentum of the orbital, or of the orbit of the electron around the atom. So when you create these energy number combinations or these quantum number combinations, they have to be unique to the electron in that atom. Now, once that electron is ionized or leaves the atom, quantum numbers don't mean anything anymore. So it's related to that particular atom. Okay, so the first one goes back to the classic Bohr orbits, the energy level, the principal quantum number N. There's no limit to the value of this in principle, but in reality there is, because, you know, it's got to be an integer value, so you're either in orbit 1, 2, 3, 4, whatever. It can go up to, you know, hundreds in theory, but in practice, when you get out to about n equals 7 or 8 or 9, that electron is so far away from the nucleus, it's very easy to knock it loose and ionize it. So you have these high energy states only in like very low density vacuum-like conditions, but they're integer numbers. So that tells us sort of what orbit we're in. Okay, what orbit. And then you have within that, you have L. Now, L is about the angular momentum of that orbit. Okay, so this is where you think about the standing waves. So you can think about the N as being the N number back in the standing waveforms, where you've got N equals 1, N equals 2, whatever. So L is how many footballs you can fit in that. So L is about the angular momentum or shape of the subshell. All right. So L is related to N. So it starts at 0 and goes up to whatever N minus 1 is. So for N equals 1, L can only be 0. For N equals 2, L can be 0 or 1, because that's N minus 1, and so on. So you can think of it as how many footballs I can fit in that standing wave number. Okay. You animals took some crazy pills last night, I think, because y'all are acting wild and y'all need to stop. Yes, you need to stop. You've been outside 4,000 times. You don't get to go again. Sorry. Okay. So it is our subshell, and when that's where you get your electron configuration numbers that you learn in chemistry class. So L corresponds to the subshell, like L equals 0 is an S, L equals 1 is P, L equals 2 is D, F, G, and then it goes alphabetically after that. So they're given a letter designation just for bookkeeping purposes in chemistry class. So that's where you get your S or P or D or F orbital or subshell. Now, if you think about the L as being about the angular momentum is a vector, right? You learned in physics 1 that angular momentum is a vector. So if you have an external magnetic field present, that angular momentum is going to be related to that magnetic field by some angle. So what M sub L does is it picks out, if you want to think about it, the orientation of that angular momentum vector to the magnetic field direction. So say the magnetic field direction is the Z direction. And so what the M sub L value does is it tells you, is that angular momentum aligned with the Z direction? Is it, you know, say at 30 degrees, 60 degrees, 90 degrees, or whatever? It sort of picks out the vector relationship between the magnetic field and the angular momentum vector. So if you have a value of L, M sub L goes from minus that value through 0 to plus that value. So M sub L being 0 means that the magnetic field and the angular momentum of the orbit are aligned. M sub L minus 1, 0, and 1 means you've got a minus 1, 0, 1. So it's like a negative component, X component, a 0, and a positive X component. And then an M sub L of minus 2 would be a larger angle. So minus 2, minus 1, 0, 1, and 2. So what it does is it looks at the relationship of the component of the angular momentum vector to the direction of the magnetic field. So that's how those three are all related. Then M sub S is its own little critter. It's called the spin. And it's useful to visualize these things like spinning around like the Earth rotating on its axis. That's probably really not the case, but it's a way for us to figure that out. So what happens is this only matters if, again, if you have an electron in an atom, because the nucleus has a spin vector and the electron has a spin vector, and they're either spin up or they're spin down. So you have two possible energy states. You have what's called parallel spin, where they're both in the same direction. They can both be up or they can both be down. Or you have anti-parallel spin, where one's up and one's down. It doesn't matter which one's which, but they're in opposite directions. Spin up is plus a half, spin down is minus a half. Parallel is higher energy than anti-parallel. So this is what an MRI does. An MRI hits the electrons with a magnetic field, causes them all to spin parallel to the nucleus. And then that relaxation time is the time it takes for them to release that energy and go back to the lower energy state of anti-parallel. And when they do that, they release a particular wavelength called the 21 centimeter line. And we use that in radio astronomy too, so the 21 centimeter line. And the time that it takes tells you about the composition of that tissue, and that's how you can map the tissue out in MRI. So that is separate from N and L and M sub L. Basically what happens is for every N, you have your values of L. For every L, you have your M sub L's. And then in each value of M sub L, you can put 2 electrons, because you can put a plus a half and a minus a half, right? So you figure out how many M sub L's you have, and then you can have double that many electrons, because you can put 2 M sub S's in each M sub L. That's how you can compartmentalize it, okay? And all 4 completely describe the electron, and they're all related. So N really determines the L and the M sub L, and then you get 2 electrons for each M sub L. Okay, and then y'all probably have seen the electron configuration notation. If you've done chemistry, you've seen the one, like, that's why it's 1s2 is the most you can have, because 1 means N is 1. So that means L can only be 0, which is S, which means M sub L is 0, but you can put 2 electrons in there, so 1s2 is the most you can have. Okay, but then P, 2p6, 2 is N is 2, so L can be 0 or 1, so you have a 2s2 and then a 2p6. So P is for L equals 1. Yes, L equals 1. I was losing my count. Then if L is 1, M sub L can be -1, 0, or +1. So 2 electrons here, 2 electrons here, 2 electrons here, 6. So 2p6. That's how that works. Okay, so what this does is this looks at the chemical periodicity of these elements. All right, because electrons are really what tell us about chemistry. They tell us about reactions and what goes with what, and is this an oxidizer or what is it, and all that good stuff. So it organizes the electrons. These orbitals organize the electrons in these columns. Okay, because everything in that same column has that same last thing. Like they all have 1 valence electron, or they all have 7 valence electrons, or they all have 8 valence electrons, or however that works. That N shell is common, or that last letter is common to all of them. And that means they all chemically act the same, which then ties into what we're going to talk about when we talk about nuclear waste, because that's why certain radioactive isotopes can be very dangerous, because they're on the same column as things that our body uses, like calcium or magnesium or sodium. Have some pretty nasty radioactive friends on down there that can get absorbed into our body, and chemically they act the same because they've got the same, last shell there. And so they bond just like calcium or sodium would, and our body doesn't know any different. It's like, oh, there's 1 electron, I'll have that. I don't care that it's on, radium or whatever. All right. So that kind of ends that little thought on that stuff. So let me stop the